Hi, my name is Sen. I'm going to present our work revisiting saliency matrix Farthest-Neighbor AUC. In our paper, we proposed a new saliency metric for the problem of center bias. Photographers tend to place the most salient object or person at the center of an image. So blindly placing a Gaussian distribution at the center may outperform some well-designed saliency systems. Our metric aims at penalizing this center bias. Saliency metrics can be roughly grouped into distribution-based and location-based. From this table, we can see that each saliency dataset may choose a different sigma value in the Gaussian filter to build density maps. And distribution-based metrics rely on such distribution statistics, so they can hardly evaluate saliency across datasets. Normalized saliency scan path and AUC variance are the most common location-based metrics. But our experiments show that the NSS is also sensitive to the sigma value. AUC-based is relatively robust in this scenario, so our method is AUC-based. A potential problem in computing AUC score is that, given the value range is from 0 to 255, and the size of a prediction could be hundreds of thousands of pixels, there will be tight values. The ROC curve could be jagged. A common solution is to add small random noise to the prediction, but this may break the relative saliency relationship. We proposed a global Gaussian smoother as a jitter to the prediction. The global Gaussian covers most of the image to break the tie. Meanwhile, the saliency relationship remains. The most salient region is higher than the non-salient. We can see the improvement in the red dashed line. But note that this improvement is model agnostic. We just expect a more reasonable and consistent output. To overcome the center bias, shuffled AUC is the most widely used saliency metric. Let's first take a look at the drawback of shuffled AUC. The shuffled AUC draws negatives from all the fixations. The main problem here is the negatives are sampled randomly, so it is very likely that the negatives are spatially close to the positives, which leads to an overpenalty on the true positives. To solve this problem, given data point, our FN-AUC tries to sample negatives from the k farthest neighbors. The neighbors are selected based on distance metric. It is easy to convert the positive side into a distribution map, and then measure the distance or similarity to find the farthest neighbors. Our method intends to avoid penalty near the true positive, but it can still penalize the center bias because the k neighbors are a subset of all the fixations. A remaining question is how we can measure the quality of the negative side. In this paper, we propose to consider the negative side as positive locations, and the center bias can be considered as a prediction map. We hope a high performance can be achieved in this case, because the negative side can greatly penalize the center bias, and we denote this as beta. Secondly, let's build a prediction map using the sampled negative and measure its performance on the true positive locations. We hope the performance can be as low as possible. The negative side can be spatially far from the positive. And let's denote this as gamma, so we can show the ratio between gamma and beta as an indicator. Of course, it's the lower the better. As we can see, the negative side of shuffled AUC is always near the center without considering where the positives are. However, our method can sample a more directional negative side. Therefore, our ratio values are always lower than shuffled AUC. Finally, we show an example that FN-AUC and shuffled AUC most disagree with. The prediction somehow covers the ground truth, but it would be blindly significantly penalized by the shuffled AUC if the positive is near the center, while the negative side of our method is more directional, so we achieve a higher performance. Thanks for watching. A fast version of FN-AUC can be found in the paper, and the pre-computed negative side can be downloaded from our paper.